Cool. Nice. We are live and we have 2 minutes to go. Do you remember if Peter's going to join us today, Jonathan?
I don't know.
Okay.
Yeah.
Cool. Well, we at least have us. That is awesome. Cool. Well, let's see. We have 8 people in. Pretty decent lineup. Nice. Let's see. I think we're set. Let's kick this thing off and see how many people we catch on the way through. Nice. We got more people joining by phone. Excellent. All right. Excellent. Awesome. Hello, everyone. My name is Scott, and I work with the Sequoia Parks Conservancy, and thank you so much for joining us on our virtual Dark Sky Festival. We are coming to you live from our headquarters in Sequoia and Kings Canyon National Parks, and we are excited to get this live Q&A going. We've had quite a journey this year, but before all the craziness started, I was able to go out to Death Valley National Park and assist in their Dark Sky Festival out there, where I met a couple people representing the James Webb Space Telescope, and we got to talking, and we were able to set up and have them come to our Dark Sky Festival, which is awesome. And that is when I met Dr. Jonathan Gardner, who is here with us today to talk about his work and his team's work on the James Webb Space Telescope. Welcome, Dr. Jonathan Gardner.
Thank you. I'm happy to be here. Happy to take questions.
Yeah,
people watch the video.
Yeah, for sure. So how this is going to go is, we have a couple guidelines that I'm going to spell out in a little bit. But as we go forwards, we hope that everybody, first off, has fun and enjoys their time learning about the James Webb Telescope. And we hope that everybody came prepared with questions. If you have any questions, please type them into the chat window, or if you're on the phone, you can wait for a pause and speak up when if you decide that you want to ask Dr. Gardner the question yourself. You can, in the chat window, just be like, hey, I have a question I wanted to ask, and we will give you the floor. We're going to keep a queue, and we'll let you know when it's your turn. If some people don't necessarily want to hear their own voice, or they're a little nervous with all the people in the chat, that's totally okay. If you'd like us to ask the question to Jonathan, that is something that we can totally do. So just let us know in that chat window, and we're gonna have a lot of fun. So first off, as you're coming in, it seems like most people are doing this naturally anyways. Please keep yourself muted. That way, we can keep the airwaves kind of clear so that everybody can hear Jonathan's response very clearly. And if you're going to ask a question, wait for a nice pause, and then you can unmute yourself, ask the question, and then please remute yourself. And as you are talking, please, before you ask your question, please say your name and where you are joining us from, and that way we can keep everybody straight and know where everybody's from. And please be patient with us. This is our first time doing a virtual Dark Sky Festival. So far, so good. It's going great, but there's a couple people on the chat, and we're like I said, we're gonna keep a queue. going so that we hopefully keep everybody in order as we go through the questions. If we miss you or the queue gets messed up, we apologize. We're going to try to fix it as fast as we can. Just give us a heads up and we'll make it as good as we can, as quickly as we can. But without further ado, it doesn't look like we have any questions queued up just yet, so I'm going to kick us off with one of my own for Jonathan. And I'm going to go with, what is your favorite anecdote about the James Webb Space Telescope project?
Okay, let me think for a minute. Well, first of all, I'm Jonathan Gardner. I'm coming from Greenbelt, Maryland, on the East Coast, and it's a nice day here today. Favorite anecdote about Webb. I think one of the things that, let's see, so I've been working on this project for about 20 years, a little bit more than 20 years, which is a long time. And the telescope's been in construction for a bit more than 12 years or so. Before that, we were developing technology and doing the design and figuring out what it was going to do. During that time in construction, assembling the telescope and testing all of the pieces and putting it all together, we've had a lot of interesting challenges from the outside world. So there was a time when we were in the middle of an important test, and there was a massive snowstorm. We had the hardware here in Maryland at that time. We had a massive snowstorm, something like 24, 25 inches of snow, and people carried on with the testing. They brought in sleeping bags and just kind of camped out with the hardware in order to keep things going. We had the building hit by lightning one time. We had, we do the assembly in a clean room, which is about 100 times cleaner than the air that we have that we're breathing right now. Maybe even bigger factor over the smoky California right now. But we had a fire in the clean room itself break out, and they all had to evacuate. And then we brought the hardware down to Houston for a test. I talked about this in the talk. While they were there, that was Hurricane Harvey, dumped 51 inches of rain on top of the Johnson Space Center. It was right in the middle of it, and there was a lot of heroics to keep that test going. This was a test that it took about a month to cool the telescope down, cool the vacuum chamber down to the temperature of the test, and so we didn't want to stop the test. We couldn't stop the test and warm up because it would take weeks to a month to warm it up. So we had people in there despite the hurricane. Real heroism. There were people that, their house was being flooded and they kept on going. There was one point where projects started running out of liquid nitrogen to keep it cold, and the president of the company, somebody called up the president of the company and they said, all right, we'll get you a shipment in even though you've got a hurricane going on. And then this year, of course, we have the pandemic. We've now got the hardware in Los Angeles, and people are continuing to do the testing, keeping the hardware safe, keeping the people safe. We had to slow down a little bit, especially people going in and out of the clean room, because the the process of suiting up to go into the clean room had been done with a whole bunch of people at once. You know, like 10 people would go in and all put on their suits together. And now that has to be one at a time because of social distancing. So we slowed down a little bit. We had to move the launch date to a little bit later in next year, but people continued to work. We never actually shut things down. And then next year, just as to see what's coming, here in Maryland, we have our 17-year cicada. So it's kind of like a plague of locusts is going to come hit us next year. I remember the last time, and they were everywhere. I think one of my favorite things is just the way people step up and kept going, kept working on the project to get our telescope ready to go into space in the launch, despite snowstorms, lightning strikes, hurricanes, pandemics, and you know, we'll have the cicadas next year. Although by that point, the telescope's a long ways away from Maryland. So
that's awesome. That sounds like quite an adventure for this telescope and for this team.
Absolutely,
really
yeah.
Cool.
And then we're going to send it 1 million miles away out into deep space.
Dr. Gardner, we have a question here from...
You just got muted.
Can you hear me now?
Yep.
Coming through all right? All right, cool. So I've got a question for you here from Jim W. Jim asks, in your recorded presentation, you mentioned there have been several times when space shuttle astronauts performed repairs or upgrades on the Hubble telescope over the last 30 years. Will that even be possible with the James Webb Space Telescope, especially with it being a cold telescope?
So good question. Thank you for that. The short answer is no. It's not going to be possible to send astronauts to Webb. For a couple of reasons. One is that it is it will be 1 million miles away. That's 4 times the distance of the moon, and therefore 4 times the distance that we have ever sent astronauts. You know, we don't have the capability right now to send astronauts out there. It's also very good that you mentioned, because it's a cold telescope. Yes, we could not put astronauts near a telescope this cold, because when astronauts and even other satellites sort of do outgassing, there's gases that kind of go out into space, and those would condense on the cold telescope and fog up the optics. That's something we have to be very careful about as we cool it down. We need to let any residual water or gases dissipate before we let the telescope cool down to its operating temperature. Now, that said, Hubble is actually the only NASA space telescope that was designed for the servicing, and Hubble and the Space Shuttle kind of grew up together, being designed around each other, with the idea that Hubble would be serviced and upgraded, repairs plus also new cameras. And so the normal way that NASA builds satellites is not planning on the upgrades or the repairs. So what we need to do is we spend an awful lot of time testing the telescope on the ground to make sure that it will actually work, and that every piece of it will work when it is out in space and operating. So that's the kind of trade-off. Hubble was designed from the beginning to be serviced. There's a price to pay for that. It's much more modular, and a lot of the mass on the telescope is put towards making things that you could insert and pull them out and replace them. We designed Webb to be much more compact relative to the size of the mirror. So one interesting thing about in comparing Webb and Hubble is that Webb is not actually as a satellite is not actually much bigger than Hubble, but the mirror and the instruments are much bigger than Hubble. So we were able to use that that size, that capability, and the mass for a bigger telescope, rather than having something that that could be serviced. In terms of mass, also Webb is much lower mass than Hubble, and we partly get that because we have the folded up telescope, and we don't have to put it so much mass into keeping everything rigid. We can move the mirrors to adjust it.
Gotcha. Thank
Thanks
you,
for the
Jonathan.
question.
Yeah. So I know you've mentioned a couple things so far, Jonathan, about the differences between the James Webb Space Telescope and the Hubble Space Telescope. Could you list off a couple other big differences between the two telescopes?
Sure. As I mentioned in the talk, the biggest differences are the temperature, the size, and the orbit. But one thing I didn't talk too much about is the wavelengths that the telescopes are able to view. So Hubble can see visible light. So the pictures that it takes are the same wavelengths of light, the same colors that we can see ourselves and that telescopes on the ground can see. In addition, Hubble works into the ultraviolet, which is light that is not only too blue or bluer than what we can see, but also it doesn't get through our atmosphere at all. So by putting Hubble into space, it was able to have, it was the first very large telescope that was able to work in the ultraviolet range. And ultraviolet tends to be the hotter stars, the stars that the biggest stars that live for only a few million years and are first formed when stars form. With Webb, we decided to push in the other direction in terms of colors and wavelengths out into the infrared. And I talked in the talk about how we have to have a cold telescope to do that. Hubble has a little bit of infrared capability, but it doesn't go very far and doesn't go as far as we can with Webb. So that's the other big difference. And that is probably the biggest reason why astronomers would love to have both telescopes working at the same time. I like to talk about Webb being the successor to Hubble, but it's not a replacement. It doesn't do the same things, only better. It does different things, and it's the scientific successor. What we learned from Hubble helped us to design what Webb could do, but we would love to have them both working at the same time. And it looks like it will. Hubble, we can't do any more servicing missions because we don't have the shuttle, space shuttle flying anymore. But Hubble is working fine, and there's nothing on Hubble that will sort of run out. All we can hope that things just keep working and don't break or don't wear out. So.
Thank you. Christina C. has a question for you. She wants to know, how expensive is the gold that went into the telescope?
Yeah, good question. It's actually the gold is on the surface of the mirrors, and it's a very, very thin layer of gold. The total amount of gold that is on the surface of those mirrors, if it was in one big lump, it would be about the size of a golf ball. As for how much that costs, that would be worth, I think it would probably be several ounces. But, you know, so in comparison to the cost of the very high-tech equipment, several ounces would be several $1,000s, not a huge expense for the gold itself. So much more expensive are things like the process for putting the gold onto the mirror, where we put the mirror into a vacuum and kind of filled that with gold, with vaporized gold, which then condensed on the surface of the mirror. That process, and you know, basically everything in the telescope is very, very expensive, and it's not so much the raw materials, but the cost of the people working on the hardware and the testing, and just the sheer number of people who are involved. We have several hundred, maybe as many as 1,000 people working on Webb throughout the world, and we've been working on it for years. So the total cost to the United States, not counting the European and Canadian contributions, is $8.8 billion. That gets us up through launch. And then after it's actually launch and what we call commissioning, which is turning everything on, and then there's additional cost of about $150 million per year to operate it, to do the science, and so forth. So in comparison to that, the cost of the gold is a small part of that. Thanks for your question.
Nice, Jonathan. Thank you. I just looked up the current running rate for gold per ounce is just shy of $2,000. So if it's 3 ounces of gold, it's probably about $6,000 US.
All right, we have another question here from Tamara Marks. She's wondering, what do you hope to be the most significant discovery with the Webb telescope?
Thanks for the question. I am most excited about the thing that I talked about in the talk, finding the first galaxies that formed in the early universe after the Big Bang. That is the research that I do. That's the research that I've done with the Hubble Space Telescope. And so I'm looking for that step of to take that science one step further and find the first galaxies that formed in a field where we're pointing the telescope. But I'd actually say that what I hope to be the most significant discovery is something that I don't know about yet. We have what we built the telescope to do, and we're pretty confident that it's going to do that. Another really exciting area is the study of exoplanets, extrasolar planets, planets around other stars, and the potential for finding things like planets that we can show that they have liquid water on their surface, oceans, or as somebody said, beachfront property, which is something that we consider to be important for the conditions for life. But again, I think what I hope will be the most significant discovery is that it will make a discovery that we don't know, that we're not predicting. And that certainly happened with Hubble. It tends to happen with every time we open up a new telescope, a new capability, with a factor of 100 times greater capability than what we had before. We end up being able to ask new questions and answer new questions that we couldn't think of before we saw the data. Thanks.
Alrighty, so it sounds like Christy Goldstone is wondering what goes into determining the appropriate launch site.
Okay, good question. The launch site for Webb is in South America. It's Kourou, French Guiana, in South America, just north of Brazil. That is the launch site that the Europeans use for the Ariane 5 rockets and other European launches. Now, in order to launch a rocket, there is an advantage to launching towards the east, because as the rocket goes up, it gets an extra boost from the turning of the Earth. So if you're deciding where your launch site is going to be, you want to think about you're launching towards the east, and then you also want to be launching over an ocean, because if something goes wrong, and we hope it won't, but if something goes wrong with the rocket and it falls back down, you want it to fall in an ocean rather than in an inhabited area. So launch sites usually are on the East Coast. In addition, you want your launch site to be relatively close to the equator. So looking at those criteria, the United States launches rockets from Florida. It's a East Coast. It's got an East Coast. They launch out over the ocean, the Atlantic Ocean, and it's in the southern part of the United States. For the European Space Agency, they actually chose French Guiana because it is an East Coast. They launch out over the Atlantic Ocean, and French Guiana is part of France. It's as much a part of France as Hawaii is part of the United States. It's an overseas canton, I think they call it. So it's launching from French soil, but being on the east coast of South America and close to the equator.
All right, thank you, Dr. Gardner. We've got another question here for you. Bob G would like to know when it will be deployed.
Okay, so the launch is November of 2021, and the deployments will all take place within the major deployments are within the first 2 weeks after launch. So the video that I showed in the talk of all of the deployments, that was obviously speeded up. It's a computer model, but all of that takes place within the first 2 weeks, the first 14 days after launch. Additionally, after that, there will be a lot more smaller deployments. We can individually control each of the 18 primary mirror segments and move each one so that they will line up and work as a single perfect mirror. That happens, we'll move them close to being in position during the second 2-week period, so within the first month. But then after that, we let the telescope cool down to its operating temperature. we start to take pictures, and we'll go through a very meticulous process of phasing up the mirrors or lining up the mirrors so that they all work together. That actually takes 3 more months. So we'll have the telescope ready to go in 4 months, and then we spend the following 2 months turning on and testing out the 4 cameras. So in all, launch the commissioning, turning everything on, getting it all ready to do science takes 6 months after launch. And when that is done, we'll have the first scientific pictures, and then it will go into doing the longer exposures, all of the science that Webb is going to do. So unfortunately, launch will be very exciting, but we'll then have to wait 6 months before we start to get the science results. And then they'll just come spilling out.
All righty, thank you. Christina C. would like to know, she's got a question about in the same sense that the Webb telescope is going to accompany Hubble or building off of the Hubble telescope, is there any chance that NASA will make a planet hunting telescope to accompany Kepler?
Good question. Actually, it's even more of a partnership than your question kind of implies. So Kepler was a planet finder. And I would say the successor to Kepler is a mission called TESS, the Transiting Exoplanet Survey Satellite. Followed on to Kepler. It was launched about 2 years ago, I think. And what Kepler did was to find lots of planets transiting, going in front of, between the star and the telescope. It found lots of those in order to determine the distribution of sizes of planets and the types of planets that we have out there. It did that by looking at lots and lots of stars in one patch of the sky in order to sort of get the statistics of what kind of planets are out there. Now, TESS is looking at the whole sky, and in particular, looking at the very brightest stars, up to stars that you can see without a telescope, and looking for, so TESS looks for planets that are transiting bright stars. And what that gives us is that it allows Webb to follow up on those discoveries, those planets, and learn a whole lot more about the planets. And because they're planets that are in orbit around very bright stars, it means we have lots of information, much more information about them than we would get from the planets that Kepler found. So the successor to Kepler is TESS. And TESS is sort of a finder scope for Webb. TESS will find the very best targets in the sky for studying the atmospheres of planets and for studying possibly even things like, would a planet have liquid water on its surface? So that's the sort of sequence. And then if you're talking about going even further beyond that, there are concepts for following up, even going beyond what Webb will do. The National Academy of Sciences right now is doing what they call a decadal survey. National Academy of Sciences will then make a recommendation to NASA and to the National Science Foundation and Department of Energy for what these government agencies should do in the next 10 years. And that could also include should NASA build an even bigger telescope than Webb, and in particular, one that would be designed to study extrasolar planets, exoplanets, in even more detail, and possibly be able to look for not just does a planet have the conditions for life on it, but would there be actual biosignatures? So the signatures in the atmospheres of planets or on the surface of planets that show that they do have life on the planet. Things like looking for methane in the atmosphere. If a planet that has both methane and ozone in the atmosphere, which is true for the Earth, that is maintained by the life on the Earth. You can get either one of those from geological activity, but in order to have both in what's called disequilibrium, it's you need to have a constant supply. And on the Earth, both the oxygen, the ozone, and the methane are being produced by life on Earth. So that would be the stretch goal. It's probably beyond the capability of Webb to conclusively show that there's an extrasolar planet with life on it. Doesn't mean we won't try, but we won't promise anything until we see the data. But future telescopes, bigger telescopes that are optimized for that kind of thing, might well be able to find that. And that would be a pretty significant discovery if we find life on another planet. Yeah, and life, of course, includes plants, plants and animals. No, we're not looking for intelligence necessarily. That's kind of a different thing.
All right, thank you. Christy G has a question related to the launch site. She wants to know why you want to launch so close to the equator.
Well, as I said, the rocket gets an extra boost because it's starting off on the turning Earth. And so the Earth at the equator turns faster than the Earth at, if you're at the pole, you're just spinning. You're not getting any boost at all. And so that's why you would want to launch near the equator, particularly to go into deep space. You want to get that extra boost from the turning of the Earth. That's why you want to go towards the east, and also the boost gets bigger as you get up towards the equator.
Excellent. Thank you, Jonathan. I have a question for you. What is your favorite instrument or piece of hardware that is on the James Webb Space Telescope?
Good question. So the 4 cameras on Webb do different things. I'll take you through them one by one, and then I'll answer your question, because it's kind of a technical part of one of the instruments, but I find it really exciting. So we have the near-infrared camera, and this works in the near-infrared. For people who are familiar with that, it goes from visible light that is gold-colored, because the gold of the mirrors absorb anything bluer than gold, out to what we call 5 micrometers wavelength. That is, if you relate it to heat, it's a temperature of around 600 degrees in the Kelvin scale. So the near-infrared camera takes pictures and is sort of the most sensitive for finding the faintest things. So that's definitely exciting, and that will be the data that, well, that will be the pictures that people will get to look at. And by the way, the pictures will look just as good if a bit different from Hubble's pictures. So the near-infrared camera. Next, we have the near-infrared spectrograph, which is a spectrograph takes the light and kind of turns it into a squiggly line where you see the light that is coming at each wavelength. And there are spikes in the spectrum that would come from particular constituents, like oxygen will emit at one particular wavelength. So you see a spike if there's the emission from oxygen, and hydrogen emits a different wavelength. So that's how you can tell what things are made of. It also, a spectrograph will also tell you how fast things are moving because of the equivalent of the Doppler effect. And that tells you, because of the expanding universe, it tells you how far away things are. So we've got the near-infrared camera, the near-infrared spectrograph. We then have a mid-infrared instrument, which does both imaging and spectroscopy at longer wavelengths, picking up at 5 microns, micrometers, going all the way out to 28.5 micrometers. So that's for the coldest things in the universe. And then the fourth instrument is kind of a specialized instrument that can do several special things. One of them is to look at transiting planets that are around the very brightest stars. Because we have such a big telescope, the other instruments will saturate if we look at a bright star in order to find this little dip when the planet goes in front of the star. So that camera actually takes the data out of focus and spreads the star over a bigger part of the picture so that we can add up the light without saturating the cameras. And then another capability is again specialized for looking for very distant, looking for the hydrogen line in very distant galaxies. Now, you asked me what my favorite component is, and my favorite component, and this is my own personal opinion, not, other scientists would tell you something different, but my favorite component is in the near-infrared spectrograph, and that is that we have a what's called a micro-shutter array, and it is a 250,000 little windows where each window can either open or close, and they're individually addressable. So what we do is we will put that on a picture that we take originally from the NIRCam or from Hubble, and we open up the little window where there's a galaxy, and we close the windows where there's just the background, or if the galaxies are lined up with each other, we would close one and open the other. And that way we'll get a spectrum where we have an open window, and we won't get contamination or background where there isn't something that we're interested in. And this means that we can take a picture like the Hubble Ultra Deep Field that I showed in the talk and open 100 windows on the galaxies that we want to study and close everything else so that we get a nice clean spectrum of just those 100 objects. So what this gives us is that in comparison to Hubble, we can do spectra of 100 things at once in a field instead of just one at a time or along a line. So that is what I think is the coolest thing. It's a type of technology called MEMS, which stands for micro electromechanical systems, and it's basically moving parts on a computer chip. And this MEMS-based micro shutter array like I said, there's a 250,000 windows, but we'll typically open about 100 at once, and it gives us the capability to study the galaxies, determine what their compositions are and their what they're made of, and how far away they are, of 100 at once as opposed to just one at a time. And the reason I'm excited about that is that the research that I do tends to be the statistics of galaxies. What are the statistical properties? And by getting 100 at once instead of one at a time, that's really exciting. Ground-based telescopes have had this type of thing for a long time, but this will be the first time we've done that in space.
That is awesome. Thank you. Looks like we have 2 questions from Tamara M. So Tamara, if you're ready, you can ask Jonathan your questions.
Yeah, hi, Jonathan. I am in Ventura, Southern California. I'm curious how many people are on the launch team, how many people it takes to get the telescope out into space. And another question that has nothing to do with the first one, but why is the mirror hexagonal versus another shape?
Okay, good questions. I don't actually know how many people will be work at the launch site for Arianespace, the company that does the launch. I know that it's kind of a remote area. It's a little bit difficult to get to Kourou, and for those who know history, the Devil's Island and the movie Papillon, that's a prison colony that was just off the coast of Kourou. There's for the Webb project, we're allowed to bring 80 people down to support the launch of our telescope. I don't know how many people normally work there, and the 80 people is limited by the number of hotel rooms they have for people staying there. The other question, why is the mirror hexagonal in shape? And that's because of the tiling, essentially. If the way optics work, ideally you want a circle. So most telescopes, the lenses or the mirrors are a circle. And that's because a circle will focus the light down to a point without too many extra spikes, or without putting too much light outside of the central focus. With the Webb mirror, so Hubble's mirror is a circle, and it has a hole in the middle because the light goes and bounces off the primary mirror onto the secondary mirror and then goes in straight through the hole in the center into the cameras. With Webb, we are making the telescope out of individual segments, like tiling and building up the telescope. So the tile in the middle, the hexagon in the middle, is missing because that's where the light goes into the instruments from the secondary mirror. Then there's 2 circles of hexagonal mirror segments. And to make those all the same shape, and yet to have something that's relatively close to a circle, the hexagon pieces are the best way of fitting that together. If we were to make them out of circles, obviously you can't put circles together and not have gaps between them. If we made it squares, square tiles are good for building up squares, but a hexagon is closer to a circle than a square would be. So if you think about like even just like tiling your bathroom or tiling another area, hexagons work pretty well at filling in the whole area covering the whole area, and you can have something that ends up being close to a circle. The hexagonal structure of the mirror also means that we have, for the primary mirror segments, we have 3 different optical designs, optical prescriptions, and then that is repeated, and the 3 different types of mirrors are then repeated 6 times all the way around. So that means that within the 18 total, we had 6 of each shape, and those would be interchangeable. If you think about the geometry of and the symmetries, it makes sense. It's maybe a little bit hard to explain.
No, that actually, your description made sense. I'm terrible at math, but I even understood that. So, so thank you. And how does it feel to be part of something that's so historic, just personally, with your career and the span of your career? What does that feel like?
Yeah, well, I'm certainly honored to work for NASA and to work on this project. I do think that it is a way of contributing, as you say, to history. It's been a long time. Like I said, I've been working on this project one way or another for 20 years, and in my current role since 2002, so 18 years. It is my career. It's my baby. I have 3 children. This is sort of my 4th child. Yeah, launch and seeing the first data come back will be very, very exciting to see that all come together, and to see what astronomers will make of it. Oh, and by the way, my father was a math teacher, and he didn't like it when people said they were bad at math. He thought that they should be more optimistic or more positive.
I can confirm through all my schooling, I am bad at math. Well, congratulations. I hope it all goes really well for you.
It doesn't look like we have any more questions in our chat queue here. Dr. Gardner, I do have a question for you. I was hoping that you would maybe talk a little bit about the experiences in your life that developed this interest in space technology in you. What maybe early experiences you had growing up that kind of got you really interested in space and led you to the professional career that you're in today?
Good question. So when I was young, I read a lot of science fiction. Like to think about, traveling to other planets, and enjoyed watching the original Star Trek, and so I guess I was always grew up interested in the world and in science. When I got to college, I was actually thinking that I might major in chemistry. And my first semester, I took a chemistry course, and there was a really, really good professor, very dynamic, and I just didn't find it all that interesting, and I didn't like the labs. And so I said, okay, I need to find something else. And then I thought about majoring in astronomy, and I took my first physics course, and I hope he's not listening, but I have to say that the professor was not very good, but I just found the subject fascinating. I thought, okay, well, if that's probably the right field. So like I said, I mean, it's a little bit unusual for undergraduates to major in astronomy. Most astronomers did physics as an undergraduate, but I actually started out in astronomy, although I did have to take a lot of physics and a lot of math. And then when I was my junior year in college, I was doing a research project with a professor, and I told him that I thought, NASA was really important, space was really important, and he was able to. He worked with some people at the Goddard Space Flight Center on a project, and he was able to help me get an internship at NASA, where I'm working now. I was an intern. And so I spent that summer and then the following summer as an intern at Goddard. And I was thinking that, a career with NASA would be great, and that's what I would want to do. I did kind of look around, and I realized that that I wanted to be a scientist rather than an engineer. And that to be a scientist, I would have to leave and get a PhD, because scientists have PhDs, engineers sometimes have PhDs, but don't always. So I knew I would have to go to graduate school and to leave. And then there was a very unfortunate and dramatic event in my senior year, which was 1986. When the Space Shuttle Challenger exploded on launch. And that was right before I had to decide where to go to graduate school. And that was actually the point at which I said, well, it looks like space is not gonna be a good career, at least not right now. And so that's when I went to Hawaii for graduate school and did ground-based astronomy, because Hawaii is a very good place for ground-based astronomy. They have the Mauna Kea Observatory. And when I was in grad school, I was able to spend more than 100 nights on the summit of Mauna Kea doing research projects, taking data, not just for my own thesis, but also I had the advantage, I guess, that my thesis advisor didn't really enjoy going to the telescope himself. So he kind of trained me up, and then I did his runs as well as my own. So I had a lot of time observing with the ground-based telescopes. After Hawaii, I went to the United Kingdom, to England, as a postdoctoral research fellow. It was originally as part of a NATO exchange program, where scientists from the United States would go to NATO countries in Europe and vice versa. And then after 4 years of being a postdoc in England, NASA had kind of recovered. This was 10 years after the Challenger accident. NASA had recovered. The Hubble had been launched in 1990, and the servicing mission, the first servicing mission was 1993, and so it was going. Hubble was going strong, and I was happy to apply for a position at Goddard to work with the Hubble. I arrived just before the second servicing mission, when there was a couple of new cameras put on Hubble in I guess it was launched in 1997. I started in 96, and then so I was there just before that upgrade and got to use some of the data from those two new cameras. And not too long after I arrived at Goddard, I was kind of walking through the hallways, and one of my new colleagues said, "Oh, hey, they're doing this new telescope. They're doing some studies of a new telescope. Maybe you'd like to come and hear this report." And I said, "Oh, well, what's it going to do?" And it said and my colleague said, "Oh, it's going to do galaxy surveys to find early galaxies. And I thought, wow, that's my research. That's what I do with Hubble, and NASA's going to build a new telescope to do that. I better get involved. And so that eventually then became the Webb. So that's how I got here.
Alrighty, thank you so much. I think we have time for just one more question, if you have time, Dr. Gardner.
Sure.
Bob G would like to know: were you able to see the total solar eclipse that passed over Mauna Kea in July of '91?
Yes, good question. I did. I was a graduate student in Hawaii at that time, and although the solar physics was not my field, what they did, the total solar eclipse passed over Mauna Kea, and all of the telescopes on the summit were doing experiments studying that eclipse. And the department, the University of Hawaii Astronomy Department, decided to bring all of the graduate students over to help out with those experiments. So, believe it or not, I was actually a shutter. So I was on the summit, able to see the eclipse, but my job was it was one of the smaller telescopes, and it didn't have an automatic opener. So the telescope had a cover on it. And the thing about sensitive astronomical instruments is, and even your eye, you should never point at the sun without some protection. So, but during a total solar eclipse, you can look at the corona. So this telescope, and I think it was a 0.9 meter telescope, it had a cover over it. They lined the telescope up with the sun, and at the moment of totality, my job was to reach over and pull the cover off. Then go through the several minutes of totality. The scientist was taking data through the telescope with their instruments, and then we had our clocks all synced up. Just before you'd start to see the surface of the sun again, I had to get the cover back on the telescope to protect the instruments. So in exchange for doing that job, being a telescope shutter, I got to be on the summit during the total eclipse, and could spend that time looking up at the solar eclipse. I've in my life, I've seen two total solar eclipses. There was that one, and then the one that was like 2 years ago, where went over a lot of the United States, including my uncle's house. So I was able to go down to North Carolina and with my family, and we could all see that one. And I'm probably preaching to the choir, but a total solar eclipse is one of those things that seeing it live is fundamentally different from seeing pictures, or it's just an experience that you can only have if you see it live. So I recommend take the opportunity. There's going to be another big US solar eclipse. I forget when, in a year or two. Maybe somebody can look that up. But if you, there we go, 2024. So it's definitely worth it. Find a good place to go and go and see it in 2024. That one's actually going close to where my parents live, although they've moved into a retirement home now. So
nice. That is awesome. That is an awesome experience, and actually a great question, Bob. Thank you for that. And it's we've been with you for about an hour now. Is there, before we wrap it up, is there anything that kind of struck your mind that you wanted to talk about the James Webb? while you're answering questions?
Not really. I'm just like to say that if you want to learn more about it, we've got a website. We've got the various social media, Facebook, Twitter, etc. Our website and our social media has a huge number of pictures of the hardware. Right now, the hardware is going through its vibration testing, and it's in the middle of that, and it's going to take a few more weeks. But when that's done, we'll be putting out pictures of the vibration table and the telescope. I've seen a couple of them that haven't been released yet. And then we unfold it all on the ground one more time, make sure it's one last time that it's all working, and then so watch our website over the course of the next year, and I hope that you are able to join in with one of our online events around the launch. We'll be doing a lot of outreach during the launch itself, and then I hope you can all look forward to seeing the first pictures.
Yeah, that's super exciting, and can't wait to see those pictures. Thank you again so much, Dr. Gardner, for sitting down with us and talking to us about this project and answering people's questions. It's been awesome to be able to engage with you and learn from you. It's been great. And thank you to all of you at home that came out and watched the video that we made and have been exploring the Dark Sky Festival. There's plenty of content. You can probably fill up the rest of your weekend with it. And, once you're done with that, we have live trivia tomorrow. Time right now, I think it's 3 o'clock West Coast, 6 o'clock East Coast, so join us for that. Same spot. You can find all that information on our website, sequoiaparksconservancy.org/Dark Sky Festival. Also, there's lots of information. There's a spokesperson for the James Webb Telescope posting great links in the chat during this entire time. So lots of great stuff at jwst.nasa.gov. for a whole bunch of information. I believe they have a way for you to send away for cool kids activities and stickers and pins and things like that. So if you're interested in anything like that, definitely check that out. And thank you for letting us bring the stars to you, and also a couple telescopes too. So thank you for joining us, and we hope you enjoy the Dark Sky Festival. Thank you.
Thank you very much for joining, and I look forward in better times to coming out to Sequoia and seeing your park.
That would be awesome.
Thank
Yeah, we have you next year if we're in person. Maybe you could come out to the park and give some talks in person. That'd be awesome. Yeah, excellent, cool. Well, thank you, everybody. That unfortunately concludes our time with Dr. Jonathan Gardner. Feel free to ask more questions on our social media pages, and we'll pass those questions on to Dr. Gardner, or you can probably go direct with him through the NASA James Webb Telescope website as well. Get some questions answered. But yeah, thank you for joining us, and we hope you have a wonderful weekend.
Thank you.
Thank you. Goodbye.
Thank you.
Bye.
Awesome.
All right. Well, thanks, Scott and Gordon.
Yeah, thank you. Yeah, it looks like most of the people are leaving. We can stay on if you have a couple things you want to wrap up, but yeah, thank you so much. This was awesome. Yeah, so we recorded this whole thing and we'll post it. I don't know if our creative director will be able to put it on by the end of the weekend, but it should be up on our website sometime next week. So it'll be all available, and you and the web spokespeople can post that on any of your media sites as well.
Sure. All right. Yeah, you can just send the links